Bound states in the continuum, or BICs, are non-radiating resonances embedded in the continuum of radiating waves, characterized by an infinite radiative Q-factor. Exceptional points, or EPs, are spectral singularities where at least two eigenvectors and their associated eigenvalues coalesce, exhibiting enhanced sensitivity to perturbations. This study reveals that multiple BICs can merge into an EP of arbitrary order, retaining the non-radiating behavior of BICs and displaying the dispersion characteristics of EPs. This novel concept, known as an EP-BIC, is validated through the numerical design of bilayer and trilayer dielectric metasurfaces operating in the visible range, realizing second- and third-order EP-BICs. The research demonstrates that these EP-BICs can be achieved by carefully tailoring the symmetry and geometry of the metasurfaces. Furthermore, the study investigates the effects of symmetry-breaking perturbations on the losses of the resulting leaky resonances, which deviate from the commonly attributed asymptotics of BICs. These findings have significant implications for the development of compact high-Q platforms for biosensing, polaritonics, and nonlinear nanophotonics, leveraging the unique properties of EP-BICs. The EP-BIC concept offers a promising route to creating ultra-sensitive and compact devices, with potential applications in various fields. In open systems, the formation of exceptional points, EPs, and bound states in the continuum, BICs, deviates from conventional asymptotics. To investigate this phenomenon, the authors employ an effective Hamiltonian formalism, describing the behavior of eigenmodes in two coupled, radiative resonators. The effective Hamiltonian features complex eigenfrequencies and coupling coefficients, which are solutions to the dispersion relation. The authors identified three possible scenarios: EPs, accidental BICs, and symmetry-protected BICs, SBICs, each with distinct conditions. Initially, they set intrinsic losses to zero, demonstrating that EPs, accidental BICs, and SBICs can arise in this system. EPs occur when modes coalesce at a complex frequency, while accidental BICs form when the coupling coefficient satisfies a specific condition. SBICs are found by decoupling both modes from the radiation continuum. The authors then explore the scenario where an eigenmode cannot simultaneously satisfy the BIC and EP conditions, regardless of the number of tuning parameters. They argue that, in a purely radiative system, BICs can only form diabolic points, unless intrinsic losses are introduced. The introduction of intrinsic losses into one of the SBICs lifts this restriction, allowing for the formation of an EP-BIC. To illustrate this concept, the authors consider a system of two coupled resonant structures, each supporting a hypothetical SBIC with identical EP-BICs of arbitrary order and the Hamiltonian for a third-order EP-BIC is discussed. The coalescence of three bound states in the continuum, BICs, into a third-order exceptional point, EP, bound state in the continuum, EP-BIC, is explored in this study. The impact of symmetry-breaking perturbations on EP-BICs of arbitrary order is analyzed using a generalized Newton-Puiseux series. A general rule is derived for the total losses of quasi-BICs emerging from an EP-BIC of order m, given by gamma h equals gamma EP plus Im, alpha 1 per meter zeta h minus 1, p1 per meter, where h denotes each quasi-BIC spanned by the EP-BIC. This rule reveals that smaller perturbations, p, lead to larger changes in quasi-BICs compared to conventional BICs and second-order EP-BICs, as illustrated in Fig. 4c. Simulations of bilayer and trilayer metasurfaces hosting SBICs coalescing at second and third-order EP-BICs confirm the possibility of coalescing BICs into EPs of arbitrary order, forming an EP-BIC. This mechanism may have broad applicability beyond optical setups, including sensing, imaging, and communication platforms. The study's findings suggest that this phenomenon is not unique to optical systems and could have significant implications for various fields. In photonic crystals, exceptional points, EPs, and bound states in the continuum, BICs, are intricately linked, giving rise to non-radiating modes that can be excited by external radiation. These EP-BICs are absent in conventional lossless systems, but their properties can be understood through the coupled mode theory of resonant states. A simplified effective Hamiltonian describes the system, and introducing radiative loss reveals the asymptotics of an EP-BIC. The separation of losses into absorptive and radiative components is crucial. Previous studies have observed EP-BICs in photonic crystals with intentional defects, harnessed them to enhance light-matter interactions, and manipulated them through external perturbations. EP-BICs can significantly enhance the quality factor of photonic crystal cavities, holding promise for applications in quantum computing and optomechanics. However, the presented model has limitations and assumptions. Non-idealities can affect EP-BICs, and further investigation is needed. EP-BICs in other photonic systems remain unexplored, and new theoretical frameworks are required to describe these phenomena. Future research should address these gaps, expanding our understanding of EP-BICs and their potential applications.